This is one of a series of videos talking about how to take measured data with uncertainties and do calculations with it. And specifically, this one is following up on several of the earlier ones we've done, especially the one talking about how you deal with some quantity squared. Oh, this was supposed to be v1 squared. But moving on and more broadly, following up on several of the earlier ones. And in particular, I want to look at an example where I want to calculate the kinetic energy 1/2 times m1 times v1 squared of this first mass before it collides with this thing. And how do I calculate that kinetic energy given all this data? Okay, so we have to break it up into several steps. We know if I want to calculate the kinetic energy by hand, well, 1/2 times m1 times v1 squared, I'm doing several steps there. I can calculate v1 squared first. v1 squared is v1 is 2.80 meters per second squared, which I think, I'm going to go ahead and do the calculation again. 2.80 squared equals 7.84. So that is 7.84 meters squared per second squared. And then I can multiply, right? Then I can say that m1 times v1 squared is multiplying that times 800 grams. I should have done this earlier. Okay, this times 800 grams gives me 6272. So 6,272. Now multiplying by 800 grams gives me gram meter squared per second squared. And then finally, I find that 1/2 m1 v1 squared is just half of that. May as well just use my calculator to do that again. I really ought to grab a calculator, some point 3136. So 3,136 gram meter squared per second squared. I guess I could have converted to kilograms at some point here and put it in standard SI units, but that's the process. You can think of this as multiple steps. And I guess I could have done all the multiplications at once, but I kind of wanted to distinguish between multiplying by m1 and multiplying by 1/2 because those were different in our process of things. So let's think about how we do all this then. I want to know what the uncertainty in this result is. What is the uncertainty in this? Well, in a previous video, we calculated the uncertainty in this v1 squared. That uncertainty was 0.564 meters squared per second squared, or approximately 0.6, but we had found it was a 7.2% relative error, relative uncertainty. And by the way, in that earlier video, I noticed that I should round this to just 7.8 to match the 1 decimal place of precision here. But for intermediate, when I want to move on and do some later calculation, always use the unrounded version to do the later calculations. Don't round off and then calculate the next one, because you'll get larger, you'll unnecessarily get rounding error in that case. So how does this work here? That means that my uncertainty here in this, remember, was plus or minus 7.2%. My uncertainty in M1 was plus or minus 1.3%. And so I can use my dominant error rule. Again, professional error analysis would do something with quadrature and all that, but 7.2% is much bigger than 1.3%. So actually, this is going to be really close to right. I can use my dominant error rule to say that I take the larger of these two uncertainties, relative uncertainties, because it's a product. 7.2% compared to 1.3, the 7.2 wins. So this one is also plus or minus 7.2%. And then in this step, I'm multiplying by a constant, by a number with no uncertainty. 1/2 is just the exact value 1/2. And so the rule there is the relative uncertainty stays unchanged. So this is plus or minus 7.2%. Now, I want to know what the absolute uncertainty of the kinetic energy is. So I can do that right now. Hang on. Once again, using this thing. This time, 3136 gram meter squared per second squared times 0.072, I get 225.7. So, okay, I'll write that down, 225.7, and then we'll do stuff with it. My uncertainty in K1 is 225.7 And then again, the units are still gram meter squared per second squared. As usual, I round this uncertainty to, ooh, it starts with a 2. Normally I'd round it to 1 significant digit, but since it starts with a 2, I'm going to round it to 2 significant digits. So this is approximately, oh, this is another interesting rule. I'm going to write this as approximately 220 gram meter squared per second squared. Some people would round up with a 5 as the next decimal place, but my rule is to round to the nearest even number with the 5 as the next decimal place. There are reasons for that. That way, half the time you'll round up, half the time you'll round down, and it won't bias your data upward on average. So, okay, 220. And so that means then when I report my result, my final kinetic energy, this has uncertainty written to the tens place, the hundreds in the tens place. So I'm going to round this to the tens place to match the last meaningful digit of my uncertainty. I kept sig figs to there, so I'm going to keep sig figs to that same place value. So 3140 gram meter squared per second squared, plus or minus 220 gram meter squared per second squared. And if I decided to convert this to standard SI units and use kilogram meter squared per second squared, that would mean that I would take this whole thing, both terms, I guess, and multiply by 1 kilogram over 1,000 grams. And that'll cancel both of the grams there. Oops, cancel both of the grams there. And I will get, well, I'm just dividing by 1,000 in each place. And notice, by the way, that I'm only keeping digits to there, sig figs to match here. So I'm going to write this as 3.14 kilogram meter squared per second squared, plus or minus, and here, divided by 1,000, 0.22 kilogram meter squared per second squared. Because remember, I rounded away that last decimal place there. I only cared about these 2 sig figs, so I only keep the 2 sig figs down there. And there we have it. That is my kinetic energy with its absolute uncertainty, and relative uncertainty is still that 7.2%. And that's what I got. Honestly, if I were reporting the relative uncertainty, probably I should have reported it as plus or minus just 7%. But for intermediate calculations, I like to keep the more precise thing until I do the final thing. So there we have it. That's my kinetic energy. And I hope that gives you an idea of how to take quantities of multiple steps, a multiple step calculation, and propagate the uncertainty through each one. You just use one rule at a time. You use the power uncertainty rule to find the 7.2%. You use the product uncertainty rule to use dominant error between those two and find that. And then you use the multiply by a constant uncertainty rule to find the uncertainty there. It's just one rule after the next after the next. It works out pretty well, and now I know how much to trust my measurement of kinetic energy.